Welcome to our presentation. Myself Sundareshwaran R. Then my batchmates are Aravind, Sujit Kumar and Vaishnavi. We designed a system for counting the object. The problem statement is the system will help and able to detect the basic objects and count them. If there are fewer objects, it will be easy for a human to count the items. If there are more than 150 or 200 objects, it will take some time to count the objects. The system will automate the task of counting the objects in many cases. And going on to the need for project, this project and the system will be helpful in small scale industries, because in small scale industries the manpower and the equipments will be less. The system will help to count the products accurately, number of products manufactured in a day accurately and in a faster way. And in libraries, the system can be employed to count the number of books in a particular rack. Usually in library there are more number of books, and librarian has to count and keep track of the books. The system would help the librarian to count the number of books in a few seconds and help them to find out how many books are missing, and helps to keep track of the books. In bakeries, there will be a display rack which consists of all snacks items like cake, bun and cookies. The system would help the bakery holder to keep track of the count of particular items sold on a particular day. Based on this data, we can able to, or the bakery holder can able to get the approximate count to bake that particular item. Then in adaptive traffic light, to implement adaptive traffic light, counting of vehicles is a necessary thing. For such application, this system can also be a solution.
Yes. Before moving into the circuit diagram, let's discuss some of the module used for our project. The main module is ESP32+CAM, and this module is based on ESP32S microcontroller with a video camera and micro SD card slot. This device is not very expensive, and it makes it handy for IoT applications involving video streaming features like facial recognition and image tracking. Here we can see the structure of ESP32+CAM. The front side of the module consists of components like micro SD card holder, which can hold a micro SD card up to a size of 4 GB, which can be useful to store images taken with the camera or to store files to serve to the clients. And OV2640 camera. This is a 2 megapixel camera attached to the microcontroller using FPC connector. This camera supports 8-bit compressed data with an image transferred rate of 15 to 60 frames per second, and flash LED. It's a white LED which acts as a flash lamp for the camera. The backside of the module consists of ESP32S microcontroller module and provision for external antenna that can be attached to improve on the strength of the Wi-Fi signal, and reset switch, and 4 megabytes of external PS RAM. Moving on to the pin configuration of the ESP32+CAM module, it has 3 ground pins. You can see the 3 ground pins here, and 2 pins for power supply. The power supply can either be 5 volts or 3.3 volts, and GPIO 1 and GPIO 3 pins are serial pins, and GPIO 0 pin plays an important role, which determines whether the ESP32 is in flash mode or not. So the ESPIO 0 pin is connected to the ground to enable this module in the flash mode, and some of the pins which are internally connected to the micro SD card is GPIO 14 pin to the clock, and GPIO 15 pin to CMD, and GPIO 2 pin for data, and GPIO 4 for data 1, and GPIO 12 pin for data 2. And let's see some of the features of ESP32+CAM. It has a low power 32-bit CPU, which can also serve as an application processor and support 160 MHz of clock speed. And it has a built-in 520 kilobytes of SRAM and an external of 4 megapixel PSRAM. This model also supports UART, SPI, I2C protocol, pulse width modulation, ADC and DAC. And it also supports OV2640 and OV7670 camera modules with the built-in flash lamp. It supports image Wi-Fi upload and multiple sleep modes. This model also supports for serial port, local and remote firmware upgrades. Unless the generic ESP32 modules, the ESP32CAM doesn't support with the USB connector. Therefore, in order to connect it with your computer, we need to use it to FTDI USB to serial adapter. In our project, we use CP2102 USB to serial converter. Here we can observe the module here, which consists of 6 pins, where it consists of 2 supply pins, either 3 volts and 5 volt, and a ground pin, and a RXT pin to receive the data, and TXT pin to transmit the data.
Let us see the block diagram of our project. So our project consists of two important modules. One is the vision and another one is the image processing system. So for the vision, we have ESP32+CAM, which is a low cost and low power IP camera, which has an on-chip Wi-Fi through which it can stream the images that has been taken through the camera over the internet. Since ESP32+CAM doesn't have an on-chip USB in it, we are powering it through a CP2102 module, which is basically a USB to TTL converter, and the programming is done through the same module through UART. The images are streamed in a private IP or even in a public IP when it comes to the cloud. So the streamed images can be got in a cloud network or even in a local host. That depends on the services that what we have. So there the image processing tasks are done. So basically the image processing tasks are done using Python in our local host or the cloud, and we are using the ESP32+CAM just as a vision system from which the images will be streamed. And after doing the image processing, we'll be getting the count of the objects, and that count will be sent to a Telegram server API through Telegram API web server, and then the count can be viewed in a Telegram bot based on the request that has been provided by the user. So this object counting system uses ESP32+CAM, and the display system is just a Telegram bot UI through which we can request, and the response will be the count of the objects which have been detected by the camera. Let us see the circuit diagram of our hardware. So in our hardware, we have these two important modules, CAM and CP2102 module. Since this ESP32 doesn't have an on-chip USB, we have to program it through UART only. So the host PC must be connected to this ESP32+CAM through this module, which is CP2102, which is a USB to UART converter. And so the connections are given VCC and the ground to power the ESP32. And the RXT pin of this CP2102 model is connected to TXT, and TXT is connected to RST, and these two pins are ideal for UART programming. So this justifies that ESP32+CAM is programmed through UART only. And when we are using the ESP32 CAM in flash mode, that is in programming mode, the GPIO pin IO0 and the ground needs to be shorted. That means the IO0 needs to be pulled down, which indicates that this can be programmed. So this connection has also to be done in flash mode when we program the ESP32+CAM. Otherwise, this can be removed.
This is the hardware setup. So you can see here we have the power bank here, and that is connected to CP2102 module. See it here. So CP2102 module, and now we have the ESP32+CAM, and this is the camera. You can see here. And here we have 4 pins as described in the circuit diagram. So we have, you can see here, right? Here we have 5V pin, ground pin, and we have transmitter and the receiver, and that is being connected to the CP2102 module. And this is the hardware setup.
Let us see the software flow chart. And so we have to reset the ESP32+CAM, and we have to check the connection. If the connection is unsuccessful, we have to reset it again and again or do something till we got the IP. So once the connection is successful, we can stream the images in a private IP address. So after once you have streamed the images, this is the vision part that is done. Once you have streamed the images, we can get the images in a local host or a cloud computing environment where we can apply the Gaussian blurring on image. That's the first step that we do in image processing in this application. So we are doing Gaussian blurring in order to remove the random noise that appears in the images. And after that, we are trying to apply canny edge detection algorithm, which will be able to detect the edges based on the frequency variations that it sees on the images. So a closed edge or a closed contour will be considered as count to 1. So the count of the objects is basically equal to the number of closed contours that it sees. But due to a random noise or due to some other object that intrudes into the view, we may get some random count. So it is always safe to take the count for many times, that is take the readings for a certain amount of time and get the mode value of it, which will be our correct reading of count of objects. And then we have to connect to a Telegram bot, and we have to check the connection whether it is successful. And once it is successful, we have to send the count to the Telegram bot through, and it will be viewed in a Telegram UI. And once the reset button is pressed, we have to repeat the process again. So this is how counting of objects happening. So the entire image processing task and the sending the count to the Telegram bot is done in local host or in cloud through Python. And the mission is done in ESP32+CAM, and that is done through embedded C. So this is how our project works.
In Arduino in order for live streaming, we have used the Wi-Fi and Wi-Fi password, and the another code is written in the Python for object counting. So this block is for object counting, and here this part is for sending the count in the Telegram app. So now let us run this code and check whether ESP32+CAM, how it is used for object counting. Here now we'll go on for detecting these two objects. So let us see how this is being detected with the help of the ESP32+CAM. So now let us move on to the screen. If you see here, if I have only one object, that is being detected. If I have two objects here, that is also being detected. Not only detection, it will also show that in the screen here. Let us see that also. So by running this code, you can see here the count 2 is sent to the Telegram app. So let us also see that by moving on Telegram app. So you can see here around now we are getting the count as 2. So hence ESP32+CAM is working as the object counter. So now let us experiment whether the object is being detected and counted at various meters. So as mentioned here, we'll measure that at 1 meter and 2 meters. So let us see whether this works. So now I'm keeping the ESP32+CAM around 1 meter, and you can see the object is being detected, and that is also verified with the camera. So now let us experiment also this at 2 meters. So now I'm having it around 2 meters. So now our ESP32CAM is detecting the object, so that can again be verified in the computer screen, and this count will also be sent to the Telegram app. Here we can see that the count is obtained as 1, so that is seen here. So even measured at 1 meter and 2 meter, the count is measured as 1, and that count is being sent in the Telegram app. So we can also verify that in Telegram app here. So you can see here the count is sent as 1. So even at different meters, ESP32+CAM is able to detect the object and count the object and send that count to the Telegram app. Thank you.